In the 17th century, one of the deepest questions in science concerned the nature of light. Did light travel instantly across space, or did it move at a finite speed? Most natural philosophers assumed that light acted without delay. When a candle was lit across a room, the light seemed to appear immediately, even across the vast distances of the heavens. No obvious delay could be seen. Among the astronomers studying this problem was the Danish scientist Ole Rømer, working at the Paris Observatory in the 1670s. Rømer was not initially searching for the speed of light. Instead, he was carefully observing the motions of Jupiter's moons, which had become valuable astronomical clocks. One moon in particular attracted attention. Io, the innermost of Jupiter's large satellites, circles the planet once every 42 hours. Each time Io passes behind Jupiter, it disappears briefly from view in what astronomers call an eclipse. Because these eclipses occur at regular intervals, astronomers use them to measure time and to test predictions of celestial motion. Yet something puzzling began to appear in the observations. The eclipses of Io did not always occur exactly when predicted. Sometimes the moons seemed to disappear slightly later than expected. At other times, the eclipse occurred earlier than calculations suggested. At first, these discrepancies were small, only a few seconds, but over time they accumulated into differences of several minutes. The pattern, however, was not random. Rømer noticed that the delays depended on the relative positions of Earth and Jupiter in their orbits around the Sun. When Earth was moving away from Jupiter, the eclipses appeared progressively late. When Earth was moving toward Jupiter, the eclipses occurred earlier than predicted. The orbital motion of Io itself had not changed. Instead, something else was introducing the delay. Rømer realized that the explanation lay in the time required for light to travel across space. When Earth was farther from Jupiter, the light from Io had a greater distance to cross before reaching observers on Earth. The signal from the eclipse therefore arrived slightly later. When Earth was closer to Jupiter, the light had less distance to travel and the event appeared earlier. From these observations, Rømer concluded something remarkable. Light does not move instantaneously. It travels at a finite speed. In 1676, Rømer presented this explanation to the French Academy of Sciences. Using the observed delays in Io's eclipses, he estimated that light required roughly 22 minutes to cross the diameter of Earth's orbit. His numerical value was not perfectly accurate, but the principle was revolutionary. For the first time, the speed of light had been measured using astronomical observations. The implications were profound. Light, once thought to act instantly, was revealed to be something that moves through space like a physical phenomenon. Later, scientists would refine the measurement, eventually determining the precise speed of light that today forms one of the fundamental constants of nature. Rømer's work illustrates a powerful theme in the history of science. Great discoveries are not always the result of searching for a particular answer. Sometimes they emerge from careful observation of a small inconsistency, a few seconds of delay in the eclipse of a distant moon. From the motion of Jupiter's satellites, astronomers learned that even light requires time to travel across the vast distances of the universe. What seemed instantaneous was in fact measurable. In revealing that light has a finite speed, Ole Rømer helped transform astronomy and physics. His discovery showed that the universe operates according to precise, measurable laws, a realization that continues to guide scientific exploration today.